podcast has to do with kind of an introduction to equilibrium. So a couple things. So far from our unit, we know that reactions have a certain rate. And typically, we can plot this. Let's just kind of come down here and look at the ink. We might have a graph. And we're going to use this equation. Let's say N2O4 turns into 2 NO2s. Alright, so we have N2O4 at the beginning, and we're just going to do this maybe in blue for N2O4. And it reacts, and as it reacts, it starts slowing down and slowing down and slowing down. Alright, so this might be over here our concentration on the y-axis. And our concentration we can use with brackets. And then down here we'll just say on the x-axis is time. So at the beginning of our reaction, we have N2O4, I'll just underline it in blue, and as the reaction proceeds, its concentration gets less and less and less. Alright, so it starts changing really, really quickly as there's a bunch of it, and as it goes for a while, it kind of starts slowing down, slowing down, slowing down. The same can be true of 2NO2, and we'll do this in red. So, there's none of it to begin with, and it starts being formed really, 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 really quickly. Alright, and again, after a while, it kind of flattens out. Alright, so notice my change, my red hopefully changed about twice as much as my blue because of my coefficient here. I have 2 moles of this for every 1 mole of N2O4 that reacts. Alright, so notice at the end, our lines flatten out. So I'm going to just highlight them in yellow real quick. So notice my red line goes flat and my blue line goes flat. Alright? The interesting thing here is that N2O4 doesn't run out. Okay? So my line doesn't do this. I'm going to change it to green. It doesn't keep going to the bottom and run out. Okay? That is not what happens. It still has some at the end of our reaction. Okay? So what we're getting into today is the idea of equilibrium. And equilibrium has to do with the fact that many reactions are reversible. Alright, so the arrow doesn't just go from left to right, or reactants to products, but we actually have 2 arrows, and our arrow also goes from products back to reactants. Alright? And we know something's in equilibrium if the rate of the forward reaction equals the rate of the reverse reaction. And really what that means is there are reactants that are turning into products at the same time that products are turning into reactants, and they're doing it equally. Alright? So notice down here in our graph that our blue decreases, 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 and then it kind of flattens out. Our red increases, 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 and flattens out. So because it's flat here and it's flat here, I know my reaction's done. Okay? But because they're flat, I know their concentrations are staying constant. So know that equilibrium is not concentration of reactants equals concentration of products. That is not true. But the rates are equal. Okay? So a couple things. Forward reactions is what we've talked about all year, and they have an arrow that kind of just goes from left to right. Reverse reactions have an arrow that goes from right to left. And typically things in equilibrium, right? Usually you have an arrow that kind of goes that way with just one slope, and an arrow goes that way with kind of one stick. So it kind of looks like an equal sign with 2 kind of tails on either end. But equilibrium is simply this idea that lots of reactions. Now there's some reactions that you can't go back, that don't go back and forth. If you burn a log, that's combustion. You burn a log, you turn stuff into carbon dioxide and water and ash. You can't make that go the other way. But there's lots of reactions that can go forward and that can go reverse. A lot of these are in our bodies, in fact. Our body systems wouldn't function unless we could reverse reactions in our bodies. So anyways, the main idea of this podcast is equilibrium. Rate of the forward reaction equals rate of reverse reaction. And kind of a picture there, know that reactants are always decreasing, products are always increasing, but at some point in time, and we might just be able to draw this, starting here, whatever time that is, that's when equilibrium begins. Okay? How come? Because both my red line and my blue line have gone flat at that point.